automatic identification system receiver for small fishing vessels embedded with intercommunication using software-defined radio and Raspberry Pi. Municipal fishermen in the Philippines experienced collisions in being rammed by larger marine vessels, wherein from 2012 to 2016, 17 collisions and 16 rams were reported. Automatic Identification System, or simply AIS, is a technology that lets a marine vessel see other vessels in its immediate vicinity. It can be a solution for these fishermen, if not for its high cost. Likewise, in emergency situations, due to limited cellular coverage at sea, fishermen do not have the means to communicate with each other and request for assistance. The objectives of the study are to provide small fishing vessel sailors a device that allows them to track the location and speed of large marine vessels while also allowing intercommunication among them. To test the performance of the system by conducting actual field tests and simulation. The input to the system is the raw AIS data transmitted from large ships and the voices transmitted from other fishing vessels. The information carried from the allotted frequency band is received by designated antennas and is processed by the Raspberry Pi microcontroller. For AIS information, the raw data is decoded and plotted by OpenCPN. For intercommunication, the voices are modulated and broadcasted by the Raspberry Pi using Pi-FM software. In addition, the Raspberry Pi will also tune into a specific harmonic frequency using the connected RTL-SDR dongle. Lastly, for the outputs, from the AIS system, the OpenCPN software outputs coordinates, velocity, vessel name of nearby ships, and their destination. From the intercommunication system, the headphones output an audible sound. Here we are at the user interface of our thesis prototype. Displayed on the screen is the title of our device, and below are the buttons that grant the user to navigate and communicate. For the purposes of this video, let's start with navigation. As you can see, the interface displayed is the open source chart plotter OpenCPN. On the bottom right corner lies the zoom in and zoom out button to manage the view of the vicinity. The red ship that is displayed on the screen represents the user's own location, and the triangles represent the ships nearby. If we hover our cursor in our ship, the coordinates of our location will appear at the bottom part of the screen just above the taskbar. This time, if we click on the ships that appear on the screen, data such as speed, location, direction, and vessel name are displayed. In this case, the vessel name of the ship nearby is BRP Batangas and is running at 0.19 kilometers per hour. If the user wishes to communicate through the built-in intercom, one may do so by clicking the communication bar at the leftmost pane of the screen. This time, the display shows a channel bar and a start communication bar. On the channel bar, the user is offered 3 more channels to communicate at, and if the user has already chosen a channel to communicate at, the start communication directly puts the user on receive mode. If the user wishes to transmit, one may do so by clicking the transmit bar. If the user is done using the intercom, one must click stop communication in order to go to the navigation mode or simply exiting the system. For the purposes of this demo, let's go back to navigation in order to show how easy it is to transition from intercom to navigation. Once the user is done, he or she may exit the system by clicking the exit bar available at every interface. To evaluate the capabilities of the device, testing and statistical analysis were performed. Moreover, fishermen were interviewed on the ease of use of the prototype. For the controlled testing of the AIS receiver, the Samyang AIS transponder was used to transmit AIS signals and was moved at varying speed and bearing. On the other hand, the developed device and the commercially available device were placed side by side and both received the signals transmitted by the Samyang AIS transponder. The speed seen by both prototypes are the same. The bearing, on the other hand, has some discrepancies of around 2 degrees for some samples. T-test was conducted to verify that there is no significant difference between the means of the commercially available AIS and the developed device. The T-critical is based from the T-test distribution table, with alpha at 0.05 and degrees of freedom of 8. Since T-value is less than T-critical, the researchers failed to reject the hypothesis. There is no significant difference between the mean of the developed prototype and the commercially available device. The latitudes and longitudes were also taken at 1-second intervals. There is a discrepancy of around seconds and tenths of seconds for both the latitude and longitude between the two devices. Similar procedures were done for the uncontrolled AIS testing. Data transmitted by actual ships in the vicinity were taken. Similar to the results of the controlled testing, the latitude and longitude received by the two devices have a difference of tenths of seconds. The speed and the vessel name received match, while the bearing angle is off by 3 degrees. For the intercommunication controlled testing, an RTL SDR was connected to a laptop with a software called SDR Sharp, which is used to measure signal strength on the frequency spectrum. The testing was conducted in an open field, and the parameters controlled were the distance and interference. All channels showed similar results. Therefore, Channel 8 was studied to prevent redundancy of data. The International Electrotechnical Commission, or IEC, prepares and publishes international standards for all electrical, electronic, and related technologies. Thus, for the intercommunication voice testing, all test values were compared to IEC standards per category. Sensitivity, upper and lower adjacency, co-channel, and intermodulation tests with 3 trials each were done on both radios. All trials that test the sensitivity and adjacent channel interference for Radio 1 passed. However, the adjacency tests for Radio 2 showed some failed remarks. For the intermodulation test, Radio 1 got passing marks, while all trials for Radio 2 failed. For the blocking tests, all trials for both radios got failing marks. All uncontrolled tests were conducted using similar procedure with the controlled. The main difference is that the powers were measured at random without considering distance and obstruction. Sensitivity and code channel tests got passing remarks, while results were mixed for adjacent tests. Blocking tests showed failed remarks. The researchers conducted one-way ANOVA to verify if the environment is a factor that affects the radio sensitivity. Since F is less than F critical, the researchers failed to reject the null hypothesis. The environment does not affect the sensitivity. For the ESOFI survey, 4 questions were asked. Based on the averages computed, question B got the lowest marking. A table that compares the price of the developed prototype with commercially available alternatives is shown. The DAISY has a lower cost when compared to the developed prototype. However, means for voice intercommunication are not embedded in the system. The Maloha, on the other hand, transmits and receives AIS signals but is the priciest among the 3.